Sensitiveness of governors. I hope you have visited my screen, right? Consider two governors, A and B, running at the same speed, all right? So this should be same type of governors. Don't compare the governors of some Hartnell and Hartung type. It should be of same type. Either porta means two porta governors. If it is Hartnell means two Hartnell governors, okay? So consider two governors, A and B, running at the same speed. When this speed increase or decrease by a certain amount, the lift of the sleeve of governor A is greater than that of lift of the sleeve of governor B. So say, for example, right, when the speed changes, we know the sleeve lift will change, right? With the increase of speed, the sleeve lift will increase. With the decrease of speed, the sleeve will fall, right? So under such circumstances, okay, it is then said that the governor A is more sensitive than that of governor B, right? So there should be a term called sensitiveness. So what does that mean? Right? So when this speed increases or decreases by a certain amount, so we know when the speed increases, the sleeve lift will increase or decrease, right? Say for example, the lift of the sleeve of governor A is greater than that of the governor B, right? So this is an incident, right? The lift of the sleeve of governor A is greater than the lift of the sleeve of governor B for a certain speed change, right? So for the same speed change, the lift is different, right? So that is the condition of the scenario you need to understand. It is then said that the governor A is more sensitive than the governor B. All right. So I'll try to draw. Okay. Say for example, at certain speed. Okay, I'll keep that speed as yes. It can be of 300 or 400 or whatever it is. A certain speed is for governor A. Okay, this is governor A. So we consider this as the initial status of sleeve, right? When the speed increases, right? When the speed increases to S1, right? There's a sleeve lift, something like this. Right? So which means the change of the sleeve lift we consider as change in A. Okay. Similar with the case of B, governor B. Okay. So for the same speed as for governor B. Okay. At the initial position, consider it as the similar height of the sleeve. Okay. So this is same height. But for the speed S1 for B, the sleeve lift is something like this. Okay. So now you can see the change in the sleeve lift compared to A. Right. So initially A was like this. When the speed increases, it was like this. Okay. Initially for governor B, the sleeve was like this. And when the speed increases, the speed was like this. But the speed is same speed, S1 and S. So initial speed S and final speed S1 for both the governors A and B. All right. So there you can see the lift of the sleeve. Right. Lift of the sleeve is high here. Or in other words, the change of the sleeve lift is high in governor A than in governor B. Okay. So this is change in the lift of the sleeve. Okay. C. I put C for change in the lift of governor B. So you can see the change in the governor A is greater than that of governor B. That's what resembles by this sentence. Right? The governor A is greater than the lift of the sleeve of governor B. Okay? The change in the lift of governor A is greater than the change in the lift of governor B. It is then said that the governor A is more sensitive than the governor B. Right? So under such circumstances, you can see the governor A is more sensitive than governor B. Why is that? Because the small change in the speed, right? For the small change in the speed, the governor A will show a large change in the sleeve lift, right? Which means we can measure it more accurately, right? In other words, this will reduce the errors, right? So that's why it is said that the sensitiveness of the governor A is more than governor B. In general, the greater the lift of the sleeve corresponding to a given fractional change in speed, the greater is the sensitiveness of the governor. Same thing, they have explained so far. The greater the lift of the sleeve corresponding to a given fractional change, right? The greater the change, right? So initially it was like this, and later it was like this. So the change could be something like this, okay? Maybe this, okay? So the change in the fractional speed, if it is great, the greater is the sensitiveness of the governor. So if this thing increases, the sensitiveness of the governor is also considered to be higher. It may also be stated in another way, right? Same thing in another way, that for given lift of the sleeve, right? For the given lift of the sleeve, the sensitiveness of the governor increases as the speed range decreases, right? So this can be stated in another way also. For the same lift, if the speed range decreases, so speed range, what does it mean? Speed range. So for a speed, it was like this. For another speed, it was like this, right? So if the speed range decreases, maybe this is 40 RPM and this is 41 RPM, right? So in that case, we see a high sleeve lift in governor A, but a low sleeve lift in governor B, right? So for a small change in the speed, a high lift, okay? Same thing in other words. But when the governor is fitted at the engine, so this is a theoretical phenomenon. We'll see what is happening in practical. When the governor is fitted to an engine, the practical requirement is simply that the change of equilibrium speed from the full load to the no load position of the sleeve should be as small as fraction as possible of the mean equilibrium speed, right? So we know the governor should be fitted in a compact space, right? So all these changes should happen within that particular small space, right? So in that case, we cannot expect a more sleeve lift like this, right? So that's a practical constraint, all right? The actual displacement of the sleeve is immaterial, provided that it is sufficient to change the energy supply to the engine by the required amount, right? So we have discussed already while discussing about the governors, the purpose is to either increase or decrease the working fluid supply depend on the load on the engine, right? So it is enough if it can regulate the working fluid supply depend on the load on the engine, right? So if the load is increasing, we need to increase the speed. Why? Because the speed will decrease automatically. So it should be capable enough to increase the speed, right? It should be capable enough to increase the speed. The actual displacement of the sleeve is immaterial, provided that if it is sufficient enough to change the energy supplied to the engine by the required amount. So it's enough. Practically, it's enough if it can change the energy or working fluid supply, right? For this reason, the sensitiveness is defined as a ratio of the difference between the maximum and minimum equilibrium speeds to the mean equilibrium speed. Okay? The sensitiveness. So now it's a definition. Sensitiveness is defined as the ratio of the difference between the maximum and minimum equilibrium speeds to the mean equilibrium speed. Right? So we know there is a mean equilibrium speed, there will be a minimum equilibrium speed, there would be a maximum equilibrium speed, right? So this sensitiveness is the ratio of these two. So it can be mathematically expressed like this. Say for example, N1 is the minimum equilibrium speed, N2 maximum equilibrium speed, and then mean equilibrium speed, right? So we know N is equal to N1 plus N2 by 2, right? Maximum plus minimum by 2, all right? Sensitiveness of the governor equal to N2 minus N1 by 1, right? So what's mentioned here, the sensitiveness is defined as the ratio of the difference between the maximum and minimum. So maximum is N2, minimum is N1, so the difference is N2 minus N1 upon to the mean equilibrium speed, right? So that is N, mean equilibrium speed. So N2 minus N1 upon N, right? This N can be replaced as N1 plus N2 by 2, right? This N can be written as N1 plus N2 by 2. So I'll replace this N with this term. So N2 minus N1, right? That's all here. N2 minus N1 upon, I'll replace with this N1 plus N2 by 2. So N1 plus N2, this 2 will come here. So 2 into N2 minus N1 upon N1 plus N2, right? So if we change it to omega, right? Angular velocity. So we know N can be written as angular velocity. So after we removing all these 2 pi and 60 and everything, we will have 2 into omega 2 minus omega 1 upon omega 1 plus omega 2, right? 2 into N2, that is omega 2, N1, omega 1, right? And 2 pi and 60 and everything would be cancelled out because all of them are there. numerical values. So at the end, what we will be having is sensitiveness of the governor is, right, 2 into omega 2 minus omega 1 upon omega 1 plus omega 2. Right? So this is what denoted by the sensitiveness of the governor. Right? Then we have another quantity, stability of the governors. Right? Stability. A governor is said to be stable when for every speed within the working range there is a definite configuration. Only one radius of rotation of the governor boards at which the governor is in equilibrium. So if you remember, right, so there is a governor. Right? So this is a simple photo governor. Right? So now we are looking at it. So based on the change with the RPM, the sleeve will lift up or down. Right? So you see at this particular speed, right, at every particular speed, there's an equilibrium, right? So say for example, right, so when we are turning it to high speed, the sleeves are moving up. When we are turning it to low speed, the sleeves are moving down. Right? So here you see this particular instrument is an equilibrium speed. Why? With the particular speed, there is no lift of the sleeve. So that speed, this is the height, right? So at this speed, this is the height. This is another equilibrium position. There is no lift, right? So similarly, there could be several equilibrium speeds, right? So for that particular speed, there is a particular height, right? The height should not change depend on the based on that particular speed, right? So for this speed, right, you see here, so this RPM, this is the height, right? So this is again equilibrium height. So this equilibrium height, when we consider it, right, so we'll now look into this statement. A governor is said to be stable when for every speed within the working range. Right? So now in this video we have seen a few speeds, right? So this is a working range. From here to here is a working range. So within this range for every speed, right? So every speed, there should be a definite configuration. What is configuration? There should be only one radius of rotation of the governor bolts at which the governor is in equilibrium, right? So these are the governor bolts, we know that, right? So for every definite speed, so at this definite speed, this should be the radius, right? So for this speed, the radius should not change up and down, right? So if there's a speed, say for example 40 RPM, then this should be the radius, shouldn't be changing. Say for example, this is 20 RPM, then this should be the radius, should not be changing, right? So this is what meant by stability, right? For every particular speed, there should be a radius, a single radius of rotation of the bolts, right? For a stable governor, if the equilibrium speed increases, right? For a stable governor, right? We can say that's a stable governor. If the equilibrium speed increases, the radius of the governor bolt must also increase. So we have seen in this video, if the speed increases, the lift or the radius will also increase. Right? The radius of governor bolts must also increase. So that's what was in here. Note, a governor is said to be unstable if the radius of rotation decreases as the speed increases. Right? So when you increase the speed here, the radius must increase. You see here, this is the radius of the bolts. It should increase. Right? When the speed increases, the radius increases. When the speed decreases, the radius decreases. Right? This is a stable governor. If it is unstable, what will happen? The opposite scenario may happen. Right? So if you see here, at this particular speed, this is a radius. Okay. So note, a governor is said to be unstable if the radius of rotation decreases and the speed increases. So we know if the speed increases, the lift should go up and the radius should increase. If it happens other way around, when the speed increases, the radius decreases, or when the speed decreases, the radius increases, such circumstances are considered unstable. Unstable. So you see here, when the speed increases, the radius increases. When the speed decreases, the radius decreases. You see here, when the speed decreases, the radius decreases. So this is a stable situation. Anything else other than this is an instability. Okay. So when the speed decreases, the radius should also decrease. When the speed decreases, you see here, the radius keep on decreasing. So this is a stable state. If the speed decreases and then the radius increases, then that is unstable. Right? So this is what meant by stability of the governors. Then we have isochronous governors. Okay, isochronous governors. A governor is said to be isochronous when the equilibrium speed is constant. Okay. If there's an equilibrium speed, then that speed should be constant. It should not keep on changing. Right. So see here, the governor is said to be isochronous when the equilibrium speed is constant. That is, the range of speed is 0. Right. So at equilibrium speed, at a particular speed, the governor lift should be constant. That is, range of speed is 0. Right? So say for example, this is a governor and it is rotating at a particular speed, right? So here is our ball, right? So the range of speed, we know what is range of speed, minimum minus maximum, or whatever it is, some velocity minus another velocity, and 2 minus n1, right? So for a particular speed, we can't have 2-3 lifts or 2-3 radiuses. Right? For all radius of rotation of the balls within the working range, neglecting the friction. Right? So if this is a speed range, or this is a speed range, for every speed range, there should be a radius, a particular radius. The isochronism is the stage of infinite sensitivity, right? Infinite sensitivity. So if there is a speed, there is a radius. If this is a speed, there is another radius. If this is another speed, then there is a radius. Okay. So there should not be any change in range of speed, right? So it should not be, for example, if this R1 is, say, for example, 10 millimeter, right? If it is 10 millimeter, then we should have a speed, maybe 40 RPM, 50 RPM, a single speed, just one speed. It can't have 40 RPM as well as 43 RPM. Right? One radius means just one speed. All right. Let us consider the case of Porter governor running at a speed n1 and n2. Okay. Now we'll just consider a Porter governor. Okay. For example, to easily understand this phenomena. Okay. Let's assume what will happen. Will it be applicable? Okay. So for a Porter governor, we know n1 squared is equal to small m plus capital M by 2 into 1 plus q into 895 by h1. Right? We have seen this equation while we study the Porter governor. Right? And for n2, which is another speed, n2 squared is equal to m plus capital M by 2 into 1 plus q into 1 plus q upon m into 895 by h2. Right? So for equilibrium speed n2, the lift is h2. For speed n1, the lift is h1. Okay. So this is Porter governor. For isochronism, range of speed should be 0. Right? So range of speed should be 0, which means this n1 minus n2 should be 0. Or n2 minus n1 should be 0. Right? That is n2 minus n1 should be 0. So if this minus this is equal to 0, this minus this should also be equal to 0. Right? So if we consider carefully this one, right? This one, what is small m plus capital M by 2 into 1 plus q upon m into 895 by h2 minus this term. What is this term? M plus capital M by 2 into 1 plus q upon m into 895 by h1. Okay. So this term minus this term should be 0, which means if you see here, this m by 2, m1 plus q, 895, all these things are similar to this and this. Only thing differing is h1 and h2, which means h1 should be equal to h2, or in other words, h2 minus h1 should be equal to 0. Right? n2 minus n1 equal to 0 means h2 minus h1 equal to 0, or h1 minus h2 equal to 0. Right? Therefore, from the equations 1 and 2, h1 should be equal to h2. Right? So if we consider this one, h1 is equal to h2. Is it applicable for Porter governor? No. Why? Because with the change in the speed, there should be a height change. Right? So this is impossible. Right? This is impossible. While the speed is changing, we can't have a single height. Right? We can't have h1 is equal to h2, which is impossible in case of a Porter governor. Hence, a Porter governor cannot be isochronous. So if you ask the question whether the Porter governor is an isochronous governor or not, no is the answer. Why? Because it is impossible to have such a relationship in Porter governor. Okay. So we'll consider another type of governor. Right now we'll consider a case of Hartnell governor. Hartnell governor running at a speed of n1 and n2. Right? So similar case, two speeds, n1 and n2, two speeds. Okay. So we'll apply the equations for the Hartnell governor, right? For the speed N1 and speed N2, right? So these are the equations which we have already studied while we are discussing about the Hartnell governor. Ng plus S1 is equal to 2fc1 into x by y. Right? So when you replace it with the final equation, you will have 2m into 2 pi n1 by 60 whole square r1 into x by y. Right? Similarly, for the velocity or speed n2, right? Speed n2, we will have 2m into 2 pi n2 by 60 whole square r2 x by y. Okay. Now we will try to equate these terms. Okay. So for isochronism, what is the condition? N2 should be equal to N1. Right? Or in other words, N2 minus N1 is equal to 0. Right? So here we have an N2, here we have an N1. Right? So if this N1 and N2 is to be equal to 0, right, we can equate it. So what we will be having is mg plus s1, right? Mg plus s1 upon mg plus s2, mg plus s2 equal to r1 by r2. Right? From these two equations, you can find y, because all the other terms are equal to m, 60, 2 pi, right? These all terms are equal. X upon y, this is also equal. So on the term differing is r2, r1, mg plus s1, and mg plus s2. Right? So from these two equations, when you equate, you will find mg plus s1 by mg plus s2 is equal to r1 by r2. Okay, this is possible. Why this is possible? mg is the same thing, but s1 and s2 are two different weights. Okay? Sleeve weight, two different weights. Similarly, r1 and r2 are two different radius. Right? So this condition can be true. Okay, but this condition cannot be true. Why? Because for different speeds, we can't have a single height. Alright. So this is why Porter governor is not an isochronous governor, but at the same time, Hartnell governor is an isochronous governor. So you can check with the other type of governors also, right? What you have to do is you just have to put the formula, right, for a speed n1 and another speed n2, and check whether you can bring it down to this condition is successful. Which condition? N1 minus N2 is equal to 0. So under such condition, if there is an equation you can find, then that's an isochronous governor. If you cannot obtain such an equation, then that is not an isochronous governor. Okay. So this is all about isochronous governors. Then we have a term called hunting. Okay, hunting. A governor is said to be hunt if the speed of the engine fluctuates continuously above and below the mean speed. So we know for every governor, while rotating, there's a mean speed. Okay? There's a mean speed. So I told you earlier, if there's a mean speed, right, it should have a radius, particular radius R1 for speed S1. It can't have two radiuses for one speed or two speeds for one radius. This is not possible. It should not be. Okay. So now we'll see. A governor said we can't if the speed of the engine fluctuates continuously above and below the mean speed. So consider if it is as a mean speed S1, it tends to fluctuate up and down, above and below the mean speed, right? Which means the radius may change to R2 and R3, right? So this is what called as the hunting. All right. This is caused by a too sensitive governor, which changes the fuel supply by a large amount when a small change in the speed or rotation takes place. So why this is occurring is, this is caused by, right? The root cause is too sensitive governor. So we'll see what will happen if the governor is too sensitive. So what will happen if it is too sensitive? We have seen the sensitiveness, okay? So sensitiveness means for a change in the speed, there should be a change in the height. Right? If it is oversensitive or too sensitive, what will happen? For a small change in the speed, there could be a very large change in the lift. Okay. So under such circumstance, what will happen? This may tend to supply excess amount of fuel, or this may stop the fuel completely. Right? So which means both extreme ends, maximum fuel supply or complete stoppage of the fuel. Right? So this is the problem with the oversensitive governor. This is caused by the too sensitive governor, which changes the fuel supply by a larger amount when a small change in the speed occurs. Right? So for a small speed change, the height change also should be something small, right? But if it is too huge, right? If the change is too huge, what will happen? Either it may end up in supplying a very large amount of fuel, or it may almost stop the fuel. Right? For example, when the load on the engine increases, so what will happen if the load of the engine increases? Usually the speed of the locomotive will decrease. Right? So under such circumstances, what will happen? The governor will give some more fuel so that the engine may travel in a certain speed. Right? So under such circumstances, okay, consider this as the circumstance when the load on the engine increases, right? So the load increases. Usually what will happen? Speed decreases. Okay. If the speed decreases, what will happen? Governor will supply some extra amount of fuel. So fuel supply will increase. So if the fuel supply increases, what will happen? The speed will again go back to its initial speed. Okay. This should be the usual phenomena. Alright. But sleep immediately engine speed decreases. Okay, you see here, when the load increases, engine speed decreases, and if the governor is very sensitive, okay. So this is the usual phenomena, but if the governor is very sensitive, okay, this is normal governor. If it is too sensitive, what will happen? It will supply much more amount of fuel, right, than required amount. Right. If the governor is very sensitive, the governor sleeve immediately falls to its lowest position. Right. So if it immediately falls to its lower position, what does it mean? The speed is almost about to zero. So what will happen? The governor will supply, the valve will supply excess amount of fuel. Why? Because it detects that the speed is almost about to drop, right? So what will happen? It will supply excess amount of fuel. Right? This will result in the opening of the control valve wide, which will supply the fuel to the engine in excess of its requirement. Right? So it will supply excess than required, so that the engine speed rapidly increases again, and the governor sleep away. So when this thing happens, right, when you supply excess fuel, what will happen? The speed will rise to a huge amount than the required speed, right? So if the speed achieve a very large amount, what will happen? The governor detect it as high speed. So what will it do? It will control the speed. How to control the speed? Again, control the fuel supply. Right? How to control the fuel supply? While the governor is going down. So when you control the fuel supply, right, what will it do? It will almost stop the fuel supply, right? It will almost stop the fuel supply. If it stops the fuel supply, what will happen? Again, the same thing will happen. The engine will about to come to a complete stoppage, right? So that's explained here. This will result in the opening of the control valve wide, which will supply the fuel to the engine in excess of its requirement, so that the engine speed rapidly increases again, and the governor sleeve rises to its highest position. Right? Due to this movement of the sleeve, so how does the sleeve move now? It's either moving to its topmost position or falling down to its bottommost position. Right? So it doesn't feel any equilibrium state in between. Okay. The control valve will cut off the fuel supply to the engine, and thus the engine speed begins to fall once again. Right? So when this sleeve falls down, right, it will cut off the fuel supply. This cycle is repeated indefinitely, right? So this will keep on going, right, indefinitely. Such a governor may admit either the maximum or minimum amount of fuel, right? So this is the issue. It won't have an equilibrium in between stages. It may either have an equilibrium at the very maximum stage, extreme end, or very minimum state, another extreme end. Right? It won't have a minimum equilibrium speed in between. This is the issue. This is what called as hunting, either maximum position or minimum position, no in between position. The effect of this will be caused wide fluctuations in the engine speed, or in other words, the engine will be hunt. engine will hunt. So this is what called as the hunting. Right? So if I can draw a huge fluctuation in speed, this is what called as hunting. For normal governor, right, this fluctuation would be something like this. Okay, speed, then bringing down to minimum speed, then bringing it up to another speed. Right, so this would be the usual case for any other governors. But for a governor under hunt, the variation or fluctuation would be huge. This would be the maximum position, and this would be the minimum position. So this would be considered as the hunting of the governor. Right, hunting. So you can see or assume it, right? Say for example, you are riding a motorbike in fourth gear, right? And immediately you bring it to first gear, like very quickly. Within a short term of gear, you are bringing it to first gear. Then you are repeating the same thing again. You are bringing it back to fourth gear very quickly. So how will you feel it? Right? You are going to a certain speed, very high speed, and then at very low speed, then again at very high speed, right? But consider another incident like this. You have a motorbike, you are riding at first gear, then slightly moving to second gear, slowly moving to third gear, and then to fourth gear, right? And decreasing it gradually, right? So that can be considered as this graph, right? So just for your understanding, I'm explaining this, right? Because motorbike doesn't have anything to do with the governors and hunting, right? Just for your understanding, I take an example of that motorbike, right? So that you can feel in your day-to-day life. Yeah. So this could be that condition, right? But if you are running from first to fourth, then fourth to one, so this could be the larger fluctuation with the speed. Right? So this is what called as hunting, right? So this is what called as hunting of the governor. And we also have two more terms, the effort of the governor and the power of the governor. The effort of the governor is the mean force exerted at the sleeve for a given percentage change of speed. Right? So we know for the percentage change of speed, the sleeve will also change its height. And it should exert some force. This will exert some force. It may be noted that when the governor is running steadily, there is no force at the sleeve. Right? Why? Because there is no uplift or downfall. Right? It will run steadily, so no need of any force. But when the speed changes, right, the sleeve also need to change its position. Either it should lift up or it should fall down. There's a resistance at the sleeve which opposes its motion. Right? So we know usually if the speed increases, the sleeve should move up. The radius of the ball should increase. This should be the condition. There should be an equal and opposite force which opposes this motion. Right? It is assumed that this resistance, which is equal to the effort, varies uniformly from a maximum value to 0, while the governors move now into its new position of equilibrium. So when you assume a governor is working, right? Play the video. Right? So at a particular speed, if you consider just a particular speed, okay? So under such circumstances, we don't need a force, right? So maybe assume this speed, okay? Now it is an equilibrium speed, which is rotating. So no need of up movement or down movement. So there is no need of any force to lift up or bring it down. But now you see when the speed changes, the sleeve will either move up or down. To move it up also, we need some force. So bring it down also, we need some force. Right? How do we provide that force? By the motion of these bolts. Right? So the force which tend to oppose this motion, right? The force which tend to oppose this motion is what called is this. Yeah, you see here at the sleeve which opposes this motion. It is assumed that this resistance, which is equal to the effort, varies uniformly from a maximum value to 0, while the governors move into its new position at equilibrium. Okay. So this is what called the effort of the governor. Then we have power of the governor. Right? The power of the governor is the work done at the sleeve for a given percentage change of speed. Right? So we know the work means the force into distance. Right? So we have a force here that is effort into the moving distance. Right? So here we need to consider the moving distance also. It is the product of the mean value of the effort and the distance through which the sleeve moves. Right? So we know if the sleeve is moving means there should be some distance from h1 to h2 or x1 to x2. Some distance the sleeve will move. Right? So that distance into this effort, which effort? The effort which the governor put to change its position. So mathematically we can write power is equal to mean effort into lift of sleeve. Right? So power P is equal to mean effort, right? Mean effort into lift of sleeve, right? Lift of